Okay, now that we have some tools, we can dive into basic algorithms. Let's say you have an array sorted in numerical order, and you want to see if a number that you have exists in this array. If you start at the front and check every number in the array, the time could be big O of n if your number is really big. The same happens if you start at the other end. You could have a really small number and it might end up taking linear time in worst case. However, we could do a cool trick here that takes advantage of the fact that you have a sorted array. Rather than starting at the end, let's say you started in the middle of the array. You could say, is my number bigger or smaller than the one in the middle? Since my number is bigger, I know that it'll have to be in the second half of the array. Now I don't even have to search the first half of the array. The best thing about this strategy is that you can make the same assumption again just on the second half of the array. Check the middle element and then move forward from there. My number is still bigger than the middle of this array, so now I only have to check the last element. And now we're at the end. We've checked 19 and 29, two numbers side by side, and we still don't see 25. Thus, we can conclude 25 does not exist in our array. Guess what? You just learned an algorithm. An algorithm is really just a high-level description of a trick for solving a problem. This one happens to be called binary search. Let's start talking about the efficiency of this algorithm with a new example. Here we have an array with 8 elements, and we're going to try and find the number 10. Okay, so we'll want to start in the middle. This problem is a little bit weird because there's an even number of elements in this array, so we could either start with 4 or 5 really. When you're designing your algorithm, you need to decide from the start whether you're going to err on the lower side or the higher side when you hit this weird case of having no real middle. I'm going to go ahead and err on the lower side and start with the number 4. Just like before, we'll check whether our number is bigger or smaller than the one in the middle. And since our number is bigger, now we only need to look at the second half of the array. Again, we have an even number of elements in our array, so we're going to pick the number on the left of the middle and start from there. Okay, since 10 is greater than 6, yet again we get to cut our array in half and deal with just the top. Yet again, we have an even number of elements, so we're going to err on the lower side and check there first. Since 10 is greater than our middle element 7, we're left with just the last element now. And now that we've checked the highest element in the array and our number is still bigger than it, we know that this number doesn't exist and we can move on. Since the time efficiency is really just the number of steps we're going to need, keeping track of each iteration is going to help us figure it out. In the past, we had to step through every single element, but here we're cutting the array in half and only considering some elements, so the efficiency isn't going to end up being as big O of n. I've created a table so we can take a good look at the array size versus the number of iterations of our algorithm. As we just saw, we had to go through our algorithm 4 times for an array size of 8. Again, we're talking about worst case here. I could have tried to put a number in between all of these places and on the outsides to figure out what the worst case was. Just to save your time, I did that before recording this video. In the process, I also discovered a trick here. If you want to make sure you're checking for the worst case, you can pick an element that's bigger than anything else in the array, and when you hit this weird middle case, always favor the lower side. You should prove this to yourself so you know that it works. But just trust me on it for now? Okay. So for an array size of 8, we have worst case 4 iterations. We can take the results from the first example too. There, it took us 3 steps to find something in an array of 7. Let's start thinking about different array sizes now. If you had an array size of 1 and you were looking for an element, say 30, it would always only take you 1 step to see whether that element was in your array or not. Great, that means we can add 1 to our table. Let's say we have an array with 2 elements in it and we're looking for this number, 23. Again, I'm taking advantage of that trick. I picked a number bigger than the ones that were in the array, and when I have that weird case, I'm always going to favor the lower side. And when my array has an even number of elements, I'm going to pick the number that's on the left of the middle. Since 23 is greater than 18, I can check 21 now. In just 2 steps, I have my answer, that 23 doesn't exist in this array. Great, we can add 2 to the table now. In the interest of time, I'm not going to go through all of these examples. You should definitely do them yourself though to prove that these results are true. Okay, we're starting to get a picture of our efficiency here. I noticed that 4 is half of 8, so maybe our efficiency looks something like this. Again, keep in mind that I'm approximating here. Instead of counting the number of overall steps in the algorithm, I'm just counting the number of times I'll need to run the algorithm. In this case 4 when my n is 8. Actually, I don't know that this is true, since half of 2 isn't 2 and half of 1 isn't 1. That's too bad. I really feel like 2 should go in this efficiency somewhere, since I have to cut the array in half every single time I run the algorithm. Let me think about exactly what that means for a second. If I cut the array in half every time I go through an iteration, that means every time I double the number of elements, I need to do an extra iteration. Actually, now that I think about it, that actually looks true with the results in my table. Every time my array doubles in size, it takes an extra iteration of the algorithm to get through it. Actually, when I represent these as exponents, I notice that the power on top of the 2 is always 1 more than the number of iterations it takes. So maybe my efficiency looks more like this? The number of overall iterations is going to increase every time the exponent on the power of 2 increases. And of course, it's only off by 1. How do I get some number or expression that represents this, the power of 2 exponent? So this is what I'm starting with, the number of elements in my array, and I want to end up with this number, the exponent. Well, I remember some weird math that I used to do a long time ago. There was this thing called a logarithm that let me express this kind of function in a different way. Instead of saying this, I could say log base 2 of 8 equals 3, and it means the same thing. Okay, so this looks a little bit nicer. I want to make a point to note that you don't need to know a ton about how logarithms work to understand this. If you just understand the equations I showed you before, you should be fine. So we could actually use another approximation to make this look even nicer. As I mentioned before, adding a constant or adding 1 doesn't really change my efficiency very much. Also, I don't really need to say that this is log base 2. In computer science, it's actually pretty safe to assume that your logs are in base 2. We often do things like cut arrays in half or use binary, so our logs are normally going to be in base 2 instead of the typical base 10. So this is the efficiency that we end up with. A little later on we'll have some more tools, so it'll be easier for me to show you visually why this efficiency makes sense. There's one thing I want to make very clear to you all right now. When I was learning about efficiency, it often seemed like people could just jump to this conclusion. They could just look at the original problem and say, of course this is log n. However, after years of being a developer, I learned that that really wasn't the case. I found that there are 3 main ways that people can get to this efficiency. One of them is just by knowing what binary search is, having seen it before, and being able to just memorize the efficiency and spit it out when you see it again. I highly recommend you just memorize the efficiency of basic algorithms for your interviews. It'll make you seem really smart if you can just spit out the efficiency from the start. However, if you're presented with a new problem and you don't know the efficiency of the algorithm already, you need to be able to solve it on your own. One way you can do that is with proofs. I personally don't like proofs and have never used them in an interview or seen other people use them in interviews. If you want to learn how to make proofs, you can look it up online and go read research papers and see other people step through that. However, my goal is to teach you the practical approach to this. When you haven't seen the algorithm already and you don't have time to whip up a proof out of nowhere, making a results table like this is actually one of the best things you can do. Creating a results table helps you notice patterns. It helps you start thinking about efficiency in terms of array size versus the number of iterations of your algorithm. When I first started learning about efficiency, I needed tables like this to see those patterns. However, after using tables for a while, I started to be able to see the patterns on my own without them. Now when I interview, I know what types of patterns are common, like changes in the powers of 2. And now I solve problems way quicker, and there are very few problems that I can't at least approach and try to solve. The worst thing you can do in an interview is say, "I've never seen this algorithm before," or "I don't know how to write a proof for it." If you're down on your luck and you really don't know what the answer is, please make a results table and try to figure it out. Your commitment to solving the problem is really going to impress your interviewer. A heap is another specific type of tree with some of its own additional rules. In a heap, elements are arranged in increasing or decreasing order, such that the root element is either the maximum or minimum value in the tree. There are two different types of heaps, max heaps and min heaps, that capture those two situations. In a max heap, a parent must always have a greater value than its child, so the root ends up being the biggest element. The opposite is true of min heaps. A parent has a lower value than its child, so the root is the minimum element. Heaps don't need to be binary trees, so parents can have any number of children. Operations like search, insert, and delete can vary a lot based on the type of heap we're discussing. Here, I'm going to focus on a max binary heap. So we're going to keep the 2 children rule, and the root will be the maximum element. In addition, a binary heap must be a complete tree, meaning all levels except the last one are completely full. If the last level isn't totally full, values are added from left to right. The rightmost leaf will be empty until the whole row has been filled. In this heap, a function that gets the maximum value, also called peak, happens in constant time. Alright, let's see what search looks like. Should we start our search by going to the left or the right? In a BST, we knew which direction to go at each step by doing comparisons. Here, there's no guarantee either way. Thus, searching ends up being a linear time operation, since normally we can't rely on tricks and we'll end up searching the entire tree. One thing to note is that we can actually use the max heap properties to our advantage in a search. For example, we can quit our search immediately if the element we're searching for is bigger than the root. In general, if our node value is bigger than the one we're comparing to, we don't need to check anything in its subtree since we know that it's the biggest. The worst case remains, but in the average case we don't actually need to search every element. The average case is closer to n over 2, but that's still approximated to linear time. Next, let's try inserting an element. We could take the approach we used with BSTs. Start at the root, then move down the tree one level at a time and do comparisons until we find an open spot. However, if our element is bigger than most of the parent nodes, or even the root, we'll need to shuffle the tree around a lot. As such, we take a different approach to inserting here. We can stick the new element in the next open spot in the tree. Then we heapify. Heapify is the operation in which we reorder the tree based on the heap property. Since we care that our parent element is bigger than its child, we just need to keep comparing our new element with its parent and swapping them when the child is bigger. We can take a similar approach to an extract operation, where the root is removed from the tree. We stick the rightmost leaf in the root spot, then just compare it to its children, and swap where necessary. The runtime of insert and delete, a more general case of extract, ends up being O of log n in the worst case. Ultimately, the worst case would involve moving an element all the way up or down the tree, and would roughly be as many operations as the height of the tree. Another thing I want to discuss is the implementation of a heap. Though heaps are represented as trees, they are actually often stored as arrays. How is that possible? Well, since we know how many children each parent has, 2, and thus how many nodes will be at each level, we can use a little math to figure out where the next node will fall in the array and then traverse the tree. Let's convert this sorted array into a tree. We know that the first element is going to be the root since it's the biggest. The next 2 elements in the array are the children of the root. By convention, I insert them from left to right. However, that doesn't really matter as long as they're on the second level. Again, each level on the tree is twice as big as the one before it, so we know the next level has 4 elements. We can do this programmatically by tracking the size of each level in a variable, then doubling it each time we move to a new level. And everything left over fills in the left side of the last level. Now you're done! Just a quick note, not every array can be represented as a heap. This one could because it was sorted in descending order. In general, the numbers need to be in an order that will make sense on a heap. Storing our data in an array can save us some space. If we use an array, we just need to store the node value and index in the array slot. However, if we created some kind of node object for a tree, each would need pointers to children and parents. So we need to store values and a bunch of pointers for every element. Since the array saves us the pointers, it saves us space. In the tree world, a balanced tree has nodes condensed to only a few levels, while an unbalanced tree has nodes spread out among many levels. The most extreme type of unbalanced tree is really just a linked list, where every node has only one child. By that definition, a self-balancing tree is one that tries to minimize the number of levels that it uses. It does some algorithm during insertion and deletion to keep itself balanced, and the nodes themselves might have some additional properties. The most common example is a red-black tree, which is an extension of a binary search tree. As is painfully common in computer science, the name turns out to be very straightforward. In this type of tree, nodes are assigned an additional color property, where the values must be either red or black. The use of color as red or black is just a convention. You really just need a way to distinguish between two different types of nodes. The second property of a red-black tree is the existence of null leaf nodes. Every node in your tree that doesn't otherwise have two leaves must have null children. As you can see, all null leaf nodes must be colored black. Next, if a node is red, both of its children must be black. There's an additional optional rule: the root node must be black. Lastly, for the rule that makes these trees actually useful, every path from a node to its descendant null nodes must contain the same number of black nodes. We'll see these rules in action when we talk about inserting. For now, know that these rules, and the last one in particular, assure that the tree never gets too unbalanced. Inserting a new node is where the magic happens. There are several different states of the tree and the node you're inserting that require different courses of action. Remember that your resulting tree needs to follow both the red-black tree and BST rules. There's a lot of information here. Your first goal should be to watch and get a sense of how red-black trees work. You can rewatch the video later to actually memorize the details. One overall rule of insertion is that you should try to insert a node as a red node, which from here on out I'll represent as both red and square to help with differentiation, and then change its color as needed. The first situation is when you're inserting the first node into the tree. Since it's the root, you can change the color to black if you're adhering to the root must be black rule. Otherwise, you'll have nothing to do. If the new parent node is black, you don't need to do any work. Since you're adding a red node, you haven't upset the balance of black nodes in any path or violated any of the other rules. Now, if the parent is red, there are several cases with more complicated solutions. If the parent and its sibling are both red, then they should be changed to black, and their parent, the grandparent, let's say, of the node you're inserting, becomes red. We switch the node colors in this way to maintain the number of black nodes in a given path. Look through all the paths in this tree. The number of black nodes in each path is still 2. The biggest problem here is that we could have violated another property by changing the grandparent. We can just treat the grandparent as a newly inserted node and change it or its ancestors according to the same cases and rules. Here, we just treat it like case 1 and change it back to black, since we still want the root to be black. In cases 4 and 5, your node's parent is red and its sibling is black. In both, you'll need to perform a rotation. In a rotation, you shift a group of nodes around in a way that changes the structure of the tree, but not the order of the nodes. Keep in mind that this is still a BST, so we need to keep our elements in strict order. In case 4, our red node and its red parent are not on the same side of their parents. Our node is a right child and its parent is a left child. Here we will perform a left rotation, since the nodes shift one place to the left while maintaining their order. At this point, we have a setup that looks exactly like case 5, where both the red node and its red parent are on the same side of their parents. Here, that's the left. We'll do a right rotation here, but this time involving the grandparent and both of its children. We need to swap the colors of these two nodes as well. Ta-da! We rearrange the nodes without changing the number of black nodes in any path. Those are all of the cases that could arise in insertion. Again, we just needed to do some clever rearranging to keep our red-black tree and BST properties satisfied. In doing the rotations, we kept any one subtree from getting much larger than the others. Insert, like search and delete, is log of n in the average and worst cases. BSTs were O of n in the worst case because they could be unbalanced. Because we're careful about staying balanced here, the runtime won't be that large.
In your nanodegree program so far, perhaps you've had moments where you felt challenged or a little bit stuck with something new that you were learning. And maybe you felt frustrated in those moments. Maybe that's even happening right now. We wanted you to know that this is totally normal. All of us face different challenges when we're learning, and the three of us thought that we would share some stories and information with you about our experiences with this.
Yeah, I can remember struggling with trying to remember what I had learned in a class I took years ago. I tried a few problems from the book I was studying and realized that I had forgotten so much and felt really frustrated. I got so frustrated I had to take a break and call a friend. But there was another funny thing that happened too. More than usual, I wanted to get the problems right. I was more motivated to learn the material better in a way that would stick with me. I also had a different perspective than when I initially took the class. From my work experiences since then, I had more ideas about when and how the information would be useful.
Yeah.
In the end, all of this made me feel good because I knew I had some new sources of motivation to tap into.
That's really interesting. It sounds like those tricky moments in your learning ended up helping you understand better how you learn best. And what about you, Eddie?
Oh, me?
Yeah.
Oh, well, I recall when I was learning about neural networks, and I realized that I didn't really understand the math that goes into training a neural network. I got confused when I looked at the code, so I began writing out the matrices on paper. I was still confused by the math, so I started drawing circles connected by lines, the way we normally picture a neural network.
Interesting.
I spent over a week drawing and scribbling simple multiplications and additions on paper until I finally reached the solution that I was expecting without all the math. Then I compared it to the linear algebra approach to see that they were the same. So even though I fell behind in my studies, it was worth it to me because I felt more confident in my ability to struggle through something and to not give up when I felt completely lost.
It sounds like all that time and effort that you took to address this big question that you had really helped you solidify your conceptual understanding of neural networks. And something that I'm hearing from both of you is that these moments of challenge ended up really providing you with opportunities to take ownership over your own learning and make it more effective for you. I think that's a super important point to talk about because if you didn't feel challenged at some points in your learning, that would actually be a big problem. It would mean that the boundaries of your knowledge and your skills weren't really being pushed beyond where they were right now. And really that's why we all come to learning experiences in the first place. The whole purpose of this nanodegree program is to help you students learn deeply and be able to apply that learning in a whole variety of different relevant situations in the future. So when we're faced with problems that build on what we've already learned but are just outside the realm of what we know how to do, our brain has to adapt to find these novel solutions, and it grows as a result. So the next time that you feel stuck or frustrated or puzzled when you're trying to figure something out, remember that this feeling is normal and it doesn't say anything bad about your ability to learn the material.
Yeah, in those moments, take a second to remember why you're here and what your goals are, and why learning this tricky stuff matters for what you want to do in the future.
Yeah.
And don't be afraid to take a break if you need to.
We'd also recommend that you identify what's most challenging and give yourself the time and permission to really explore it in detail. Remember not to rush yourself because we want your learning to feel cohesive and to last.
Totally. Keep giving your brain those opportunities to grow. Happy learning.